LPI virtual seminar this week. And I appreciate you all showing up at the new time. So the virtual seminar will be at 3 p.m. Central from and then going forward, and that's just to help accommodate people's schedules in different time zones. So our guest this week is Dr. Michael Thorpe. He's a NASA postdoctoral fellow at Johnson Space Center. Got his PhD from Stony Brook University, and his research is on the superficial history of Earth and Mars using sediment and sedimentary rock compositions. So I'll go ahead and turn it over to Mike, but just as a reminder, please mute your microphone if you're not the speaker. If you have any questions for Mike, you can type them into the chat, and we'll address them in the last 15 minutes or so of the presentation, or you can ask them directly then. So with that, thank you, Mike. Take it away.
All right, great. So thank you for having me. I think I'm going to do a quick sound and tech check. Everybody can hear and see me? Thumbs up. I can't see you, so okay, great. And here we go. So yeah, I normally include a brief introduction slide here, but Sean just did a really great job. Introduced me. I will note that I've moved on from my postdoc now and was fortunate to get hired by Jacobs, contractor to NASA JC, as Mars sample return scientist. And that's my current role now. And I'm kind of fresh in that position, but really enjoying it, and hope to detail more about Mars sample return at some point in the near future. I also want to throw up this acknowledgement and collaborator slide, because without these funding sources, as well as the number of collaborators, I wouldn't be anywhere to present what I am presenting today. I have a few of the noteworthy names in the top right corner there, but there's many more that I'm certain I'm missing. And I would just like to pay gratitude to all these important people in the funding agencies. So it's a pretty broad title that I have here, Exploring Mars with Curiosity and Earth for Sedimentary Cues, because this is really the kind of motivation driving my research. So I figured I'd frame it into a talk here, and we're going to start by looking at the sedimentary rock record of Mars. And this rock record is ancient, and it's fundamentally different than what we see on Mars now, and it's also fundamentally different than Earth. So we're going to explore this, and I think it's going to be pretty fun. So sit tight, and we'll explore it with Curiosity, which is the Mars Science Laboratory rover, and it's in Gale crater. And we're going to look at the geochemistry and the mineralogy that come back from this rover and try to unravel a complex sedimentary story. Lastly, I'm going to touch on some terrestrial analog studies because I think that the planets go back and forth. They really help us understand each other, and use Earth as a reference frame to understand what's going on with ancient Mars. And so I threw up this sticker point, the Hutton unconformity picture in the background here, because it just really sticks with me that the sedimentary rock record acts as a continuous movie of Earth's history, and the stratified record provides a rationale, almost a complete documentary of what's going on with the planet history. And Hutton's unconformity here derived a fundamental principle that the present is the key to the past, but for the sake of planetary science and for the studies that we're looking at with Mars, can we say that Earth is the key to the past Mars, and then vice versa? Can Mars give us some clues into early evolution of water in our solar system? And so the history of water on Mars is been around for quite some time, and this is one of my more favorite pictures from orbit here of Ibris-Waldi, which is a beautiful delta showing that you have running water into a standing body of water, creating these unique shapes that are most diagnostic of a delta. But the history of water on Mars didn't originate with this. It originated with these canales that were drawn back in the day. They were wrong, but they were at least considered a unique way of seeing channels on the surface of Mars. And since then, the evolution of identifying water on Mars has evolved all the way from Mariner 9, identifying valley networks, to on the right here, we have the Mars Reconnaissance Orbiter and HiRISE images making these really beautiful delta mosaics from HiRISE images, and just giving us these detailed images that we've never seen before. And so not only do we see this from orbit, we also see this in situ. And this is the backdrop here of the Burns Formation, which was explored by the MER rover. And you can see that the water signature here is preserved in the rock record, as we have layers throughout the sedimentary rock that could have been influenced by groundwater at some point. And then there's also evidence for aeolian deposits as well. So it's a complex story just from seeing the stratigraphy here. And then not only do we see it in the stratigraphy, we see it in unique outcrops where we had these famous Martian blueberries, as well as these delta deposits, which we'll talk more about at Gale Crater, which are showing the clear evidence that water was quite prevalent on Mars at one point. But what point was that? So if we plot here geological time going from left to right, Earth is in blues and greens, and just below that is the Martian geological time in reds and orange here. And we can see that most of the rovers are exploring terrains that are quite ancient. And so they're rather old. The sedimentary rock record is significantly older than what we see on Earth. The oldest metasediments we have are 3.62 years old. But the real kickoff of kind of terrestrial basalt weathering doesn't start until the rise of the biosphere. And so Mars' sedimentary rock record is fundamentally older than that of Earth. And what can that tell us about the evolution of water in the solar system is something that we'll try to tackle a little more. And so we're diving into the sedimentary systems here, but I want to talk about it with a bit of a geochemical and mineralogical slant. And you'll see that this talk is heavy-handed towards that because those are my specialties. And so here's a simplified box diagram of the source system with the source area up here in the top corner here. We create sediment and we can unravel the various processes with the mineralogy and the geochemistry of weathering and erosion, the secondary assemblages, as well as provenance, potentially paleoclimate, which we'll touch on more. And then we transport these. And during this transport process, we get mixing, sorting, continued alteration, and then we get neoform minerals as well as inherited minerals, detrital minerals, eventually deposited in sedimentary basin where orthogenesis and diagenesis kicks in. All of this can be unraveled with geochemistry in mineralogy. And it also has a sedimentological bias too with grain size, grain shape, and fluid carrying capacity. So kind of bringing all three of these areas into focus helps us unravel what's going on from source to sink. And it emphasizes the importance of mineralogy. And so not only from orbit do we have features, landforms that show us that there was water running on the surface of Mars, we also see it from remote sensing techniques where this is a review paper by Bethany Elliman in 2014 showing the spread of secondary minerals that were formed during sedimentary processes. My favorite happened to be phyllosilicates, but we also have carbonates and sulfates, chlorides and hydrated silica here displayed, which overlap with a lot of the features that we saw before from orbit, the deltas and what have it, just showing you that the mineral assemblages are coinciding with this too and just elaborating on our story of water. And again, not only do we see this from orbit, we see this in situ with the ChemIn instrument that's on board. The Curiosity rover has identified that clay minerals are quite present in the fluviolacustrine rocks that we've examined, ranging from as low as 3%, but as high as 34% clay minerals. So really cool stuff here. And if we throw our blueberries back up there, we can see that although there wasn't an X-ray diffractometer on board the MER missions, we were able to identify with Mossbauer by Dick Morris and all that these were hematite-rich spheres. So again, just showing strong evidence that water played a huge part in the history of Mars. So if we then plot these minerals, and I took a few here for liberty of just the ones that I'm really interested in. These are clays, iron-bearing smectites, and phyllosilicates, as well as amorphous materials. And plot where we see them. It coincides with where the rovers are. And we compare to where we see similar minerals on Earth. These minerals, the clay mineral story really doesn't start to happen until late Precambrian. They call it the late Precambrian clay mineral factory, where smectites start to make an appearance, and these one-to-one phyllosilicates are kind of less abundant than what we start to see. And so this is really just emphasizing the point that not only is the Martian sedimentary rock record older than what we have on Earth, it's preserving juvenile secondary minerals. And this could be important for unraveling what history has to tell us. And can this mineralogy help us characterize past aqueous environments? And so from orbit and in situ, I think I convinced you that we have seen plenty of water, but what does this tell us about the sedimentary history? And Mars was fundamentally different, but what does this mean for how it evolved? And so sediments journey from the mountains to the shores. This is kind of a different representation of the source sink system that I showed you before, where we're just carrying the sediments across and the various mechanisms that can change its composition. But when we're on Mars and we have a desiccated landscape, how do we know this happened? Well, we have a rock record here that shows us the progression from fluvial, which we see are conglomerates, to lacustrine, which we see are mudstones, the progression of these sedimentary rocks in the system, in the sink here, showing that there was this fluvial lacustrine system. And so where might you land a rover to study this kind of system? It's where we've landed rovers in Gale crater and where we landed in Jezero crater in the delta, in the sink itself, and begin exploring there, similar to how we would do field work on Earth, which I've done in Iceland, these kind of source to sink studies where you start at the sink and work upstream. And so I will go to our first source to sink on Mars, and this is Gale crater, which I've showed this image before, but just to blow it up a little bit here, this was in Grotzinger 2015, where we have these sandstones in the foreground here, and in the background we have these laminated mudstones, just emphasizing again this fluvial lacustrine history. And we're going to explore these rocks with the Curiosity rover. And so the Curiosity rover landed in 2012 and has been traversing the river and lake sedimentary rocks for a number of years now. And MSL was designed to undertake the search for past and present habitable environments. And so we're going to focus on some of the results that are returned from the CheMin instrument. I'm recently very lucky to join the CheMin team in 2018. CheMin stands for Mineralogy and Chemistry and Mineralogy. It's part of the 11 instrument payload on the Curiosity rover. It's an X-ray diffractometer that returns these amazing X-ray diffractograms here. These are the first XRD results on Mars ever. So really exciting stuff. And the CheMin team takes these diffractograms and makes them one-dimensional, and we determine the mineral abundances from these patterns. And so here's the history of the traverse of Curiosity. It started up here in Yellowknife Bay. This was Sol 3, which is a solar day. It's a little longer than a terrestrial day here on Earth. And so Sol 3, 2012, we landed in Peace Vallis, or just outside of Peace Vallis here, which if you can squint your eyes, you may be able to see this delta feature here, or this alluvial fan here. I will highlight it a little bit to help your eyes if you can't see it. But this is where we landed, just outside of that. And we began our traverse towards Mount Sharp. And we are here to date. This is Sol 3049. We've traversed so far approximately 25 kilometers. And I joined the team right around here, Verruben Ridge, which we're going to talk more about around Sol 2000. And so for the rest of the talk, we're going to kind of focus on this area, Verruben Ridge, up to the Green Hue Pediment in particular, because this is stuff that I'm more familiar with now since being on the team too. And so this region actually is designated as the clay-bearing region. And the clay-bearing region was a real critical rationale for landing in Gale crater to start, because clays are commonly formed on Earth in very neutral environments, and they're a very common secondary product from basalt mineral weathering. And so this was a reason for going here, and in a sense touching down. It was informally dubbed the Glen Torridon region. It's in a little trough here after Verruben Ridge, and we have the Green Hue Pediment to the right here. And we started traversing, if you will, this pay dirt area at the end of 2019. And this is a bit of a different perspective here. Now we have the Verruben Ridge up here. The member is called the Jezero, the pediment over here. And this is the Glen Torridon region, outlined with all these stars, which are actually the drill samples that we took. Each drill has a unique name. So we have Kilmary, Aberlady, and so on and so forth, and a number of different drills over here. And we really did a great job, I think, of interrogating this terrain with an extensive set of drill campaigns. And that's what we're going to review today. And so the drill campaigns, these are all the drills we had. And if you can squint your eyes a bit, you can actually see the rover here with Aberlady and Kilmary drill targets right here in two different blocks, showing you where these drill locations are. I think it's always nifty looking at the drill holes, and just the various colors are eventually going to tell us about some of the minerals that are in them as well. But if we look at the stratigraphic column here and I plot it where these drills are, and this strat column comes from Chris Vetto and the Sed Strat team. And we can see just from at least the drills in the strat column here that VRR, which is which is abbreviated for Vera Rubin Ridge, and Glen Torridon, abbreviated as GT, are syndepositional, so we're deposited at the same time. However, VRR is more resistant to erosion, and so this has something to do with the sedimentary history. And then on the flip side, we have this pediment area over here, higher up, that is composed from Aeolian sands and is also resistant to erosion, more resistant to erosion compared to the Glen Torridon region. And so seeing what the resistivity of these materials or how friable they are to weathering is going to have a unique input on what the sedimentary story is. And so if we just look at the X-ray diffraction patterns, and so this takes that pretty picture before of all the rings and makes it into a one-dimensional pattern here, and it's plotted versus the intensity is plotted versus the source. The source is reflected off the lattice planes, and that's what we have plotted here. But the secondary x-axis is also angstroms, so that's the distance between the lattice planes. And you'll hear me talk about angstroms a little bit, so I want to throw it up there so that you were familiar in terms of where we were talking about. But if you look at the patterns for the 8 drills that we have in the Glen Torridon region, you'll see that they're really largely in the same mineralogical family. And that's really to say that we have plagioclase, pyroxenes, smectites, amorphous materials, as well as calcium sulfates. For anybody that's curious, the amorphous materials are identified in this kind of scatter above the background. The background should be kind of consistent across, and it's scattered above there. And furthermore, the similarities here, the primary basaltic mineralogy is dominated by plagioclase, and that's just to say that plagioclase is more abundant than pyroxene. And then lastly, phyllosilicates, which are identified by this broader peak down here, these are the most phyllosilicate-rich samples to date, and we have some phyllosilicate samples, the Glen sample itself, coming in at 34 weight %. So really exciting stuff. The differences are a little harder to see, so I'll try to identify some areas of interest to look at, but these mineralogical differences could potentially be tied to the sedimentary history. And so we have siderite here, which we're going to talk about more, which is an iron-bearing carbonate, as well as hematite identified here with this peak, and then this new 9.22 angstrom phase, which has never been identified before. It's unique to the Glen Torridon region, and all these differences together, I think, have the ability to provide clues to what's going on with either diverse provenance, weathering intensity, and/or various diagenetic episodes. So we'll focus on the differences here for a few minutes here. And the first difference is the siderite detection. And this is the first definitive detection of carbonate by Chemin. We've speculated that it may be elsewhere, but this is the first time that we've been very confident that this is siderite and an iron-bearing carbonate. And it's been identified in 3 samples to date. And the interesting thing for me is that siderite is stable in near neutral environments. And this is just a stability diagram showing where siderite commonly falls in terms of pH. And this is looking at kind of, this paper was trying to tackle the ancient atmosphere of Precambrian environments. Siderite is commonly found in Precambrian rocks and is commonly associated with minerals such as minnesotite and greenolite. And so that's an interesting thing to see these associations and the type of environments that they're associated with. And then on the right here, we're looking at iron oxides, and I have the various drills going from Vera Rubin Ridge to the pediment with Glen Torridon in the middle here, and I have hematite in red and magnetite in gray, showing you the differences in iron oxides as you're going from these different regions. And you can see that Vera Rubin Ridge is enriched in hematite, as Glen Torridon doesn't have much hematite and not much magnetite at all. And then we get into the pediment, which has a ton of magnetite and a little hematite closer to the contact itself. So iron oxides certainly play a story in unraveling what's going on here. Then we have this new phases, this 9.2 angstrom phase. And so for me, when we entered into this clay-bearing region, this Glen Torridon region, it's the most phyllosilicate-rich region to date. It initially lends me to want to see more phyllosilicates, and that's what I was hopeful to start. And also, this initial peak position here at 9.2 angstrom is very close to smectites, another phyllosilicate here. So it invites an immediate interpretation as a talc mineral. But as you see talc plotted here, where the main peak would be, as well as an iron-bearing talc, which is also known as Minnesotite, don't exactly line up with this 9.2 phase. And so something needs to be explained to kind of reconcile why these don't exactly line up. However, if you do mix a phyllosilicate with another phyllosilicate, which is commonly seen on Earth, some examples are smectite and illite. It's a kind of a transition from low temperature phase smectite to potentially diagenetic maturation of smectite to illite. You do see mixed layers a lot in those. We don't see this kind of talc mixture that I'm proposing yet, but if you model it, you can indeed get this 9.2 peak, which is a talc mixture with a 7 angstrom phase, which could either be serpentine or greenolite. I happen to like greenolite as being the mixture phase here because it's commonly associated with siderite in environments, and it's in near neutral environments, which is kind of clay's comfort zone here. So this is one possibility. I will note here, though, that there are plenty of other possibilities. And so we have a list here that the Chemin team is still really looking at quite diligently, and we're exploring with every tool that we have in the shed. But for the sake of this presentation, we're going to go forward with this model that it is a mixed layer phyllosilicate, but keep tucked in the back of your mind that it's still out for debate. And so here we take the regional scale, and so I have our hematite abundances and our phyllosilicate abundances, and then I have our various members here going from VRR to the pediment with Glen Torridon in the middle here, showing you the differences as we go from one unit to the next, as well as our key identifications of minerals here. And I want to use this as a sedimentary criteria for developing conceptual models. And these conceptual models need to include, at least in the way I'm approaching it, they need to include the clays and iron oxides, as well as our key detections, and also try to reconcile it with some geochemical considerations. And so here I have in blue chemical index of alteration, which we'll dive into more later on, but it's a kind of a quantitative measure of the degree of alteration in the samples. And it kind of coincides with phyllosilicates, but any story probably needs to reconcile what's going on with the geochemistry and the mineralogy to tie it all together. And so here's the regional conceptual model that I've been working on, developed from our sedimentary criteria here, and it's complex. And so we have a lot going on, and I think that's the fun part here, and unraveling what's going on with the criteria I have here has been a very interesting thing to try to tackle. And so here we have various episodes, and I'll go over each one of them, and we'll focus on one in particular. We have T1 here, which is kind of the deposition of detritus, and then this detritus is eventually altered in some fashion with orthogenesis. We then have T2, which is lake waters, which we're going to propose are saline lake waters that are infiltrating into the sediments that are mixing with groundwaters. And this is creating a unique geochemical from which you'll see on the next slide. We have T3 over here, which basically shows that the sedimentary rocks are different within the Glen Torridon based on the proximity to this mixing zone. So how close they are to this actual mixing zone. And lastly, we have T4 over here, which are these aeolian sands, which comprise the pediment. They were laid down and eventually altered with groundwater, but not in this mixing zone, so in a different fashion. And one more thing, not pictured here, is T5, is baryodiagenesis needs to be invoked for at least a portion of this, but we're not by any stretch invoking high temperatures, kind of still low temperature baryodiagenesis. Maybe less than 80 C or so would potentially change some of the phases that we need to see in this kind of model. But this would take forever to explain, so I'm going to just focus on my favorite piece of the puzzle here on T2, the saline and groundwater mixing portion of it. And I have our sedimentary criteria up here. I zoomed into this little piece of T2 over here. And we have our different regions. We have sub-VRR, we have the VRR, Verruben Ridge samples here, and we have the GT, the Glen Torridon samples here. And if we go back to our stratigraphic models saying that these are syn-depositional, so VRR and GT are deposited at the same time in a similar environment. However, they are altered in a different fashion. And one mechanism to do this is taking groundwater, which we're proposing is anoxic, silica-rich, and circumneutral, and mixing this with infiltrating saline waters, which are suboxic, silica-poor, and alkaline. And this creates two things: a density-driven circulation, so you mix and then you dry back up, and it creates a unique geochemical front that's going to create a unique mineral assemblage. And if we kind of take some of the minerals that we're seeing from ChemMin, or at least think we're seeing in our modeling that we're seeing, we can see that this model may be able to explain the differences between them. And we have our iron talc here in the very rare Rubin Ridge with our plethora of hematite, as well as iron talc and greenolite, our mixed layer phyllosilicate, if it is this phase in the Glen Torridon region, associated with our carbonate. And then the groundwaters didn't infiltrate, or the mixing zone didn't penetrate into the sub-VRR samples here. And so this is, if you want to dive into it more, it's a complex regional story. I don't expect you to look at all of this. I just want to show that it's a working model that takes a lot to explain what's going on with this regional story. But the thing to examine here is that there's a sharp contrast with the adjacent units. And Glen Torridon's enrichment in phyllosilicates suggests that clays play a critical role in shaping this landscape. One mechanism to produce these changes is the saline subsurface circulation mixing with groundwater. And if you ever want to talk about more of this, I obviously love to chat about this, and this model is quite complex, so feel free to contact me. And so one thing I'll point out here is that we have terrestrial examples of these things. We have modern mixing in saline lakes on Earth, as pictured on the left here. We also can go to the ancient record, and we have Precambrian models for ancient seawater mixing, where we see things like greenolite precipitating in the sediments. And although the sedimentary rock record of Gale is complex, some would argue the sedimentary rock record of Earth is equally, if not more, convoluted. And so the tale goes both ways, and while we're using terrestrial examples to place context on Gale crater, we need to continue to explore analogs on Earth for Mars, and there's nothing perfect, but we can continue to try to expand these efforts. And so Mars was once Earth-like, but what does that really mean? And we don't really know temperature constraints, precipitation, kind of altitude, or distance from the source that these sediments traveled. And so these are all variables that we can try to explore. And it's not a one-to-one relationship, and that's what this figure here is trying to do. Just check my time here. Okay, is that it's a tale between two planets, and they're fundamentally different in the sense that Mars is composed of basalt. It's dominated by basalt. It's dominated by this secondary crust, whereas Earth is really the only planet that we know of really that is composed of this tertiary crust that happens because of plate tectonics. So if we go to this map of Earth on the right here, in red are these areas that are mafic or basaltic in composition. We can see that they're not that abundant compared to these gray areas, which are not specify what their composition is, but by and large, the Earth crust is dominated by a granite dioritic kind of crust. And so we only have a few areas to go, and we have to go to these basaltic areas to kind of understand what's going on with the Martian sedimentary rock record as well. And this kind of fundamental difference in provenance is going to be highlighted in the expected sedimentary trends, particularly when we look at weathering profiles. If we look on the left here for Mars, we have different primary mineral assemblage compared to the weathering profile on Earth on the right, which is composed of quartz and feldspars. And these primary differences are going to lead to different sedimentary trends as well. And so it's emphasized with basalt being more efficient at weathering. They also form variable secondary phases, and they have different buffering capacities for groundwater. And so the difference in provenance is going to be exacerbated in the sedimentary trends that we're expected to see. So one of the part of my PhD, or most of my PhD, and then leading into some of my postdoc here, we worked on building a terrestrial reference frame for basaltic weathering on Earth and exploring the variables that influence it. And so there's only about 5% of landmass available to weather that is basalt. So an attempt to build the best terrestrial reference frame I could, I tried to tackle as many of these basaltic environments as I could, and span this a range of climatic regimes. So we go from cold to warm, as well as dry to wet. And we looked at both fluvial basaltic sediments as well as weathering profiles in basaltic terrains, and try to explore what variables were impacting the extent of chemical alteration. And so we come back to this chemical index of alteration, the CIA value. It's the most widely used chemical weathering proxy on Earth. And it's been speculated that no chemical weathering proxy has more widespread application to the Martian sedimentary rock record. So that's what we're going to use here to kind of classify the degree of alteration. It's represented here by the elemental ratio here, which is really just looking at mobile elements over immobile elements over mobile elements. And so the higher the CIA value, the more altered you are. And here's the scale over on the left, showing you going from igneous rocks, which have composition or CIA values around 45, to feldspars at 50, all the way up to kaolinates would have intense weathering at around CIA values of about 100. And so this CIA value is not only seen in nature. This is on the diagram here representing a Terney diagram of the CIA. This is the ACNK diagram, which the CIA would plot as a vertical extent on this diagram. And so you can see this in nature, going from unweathered source materials to weathered residuals. And you can also see this thermodynamically. If you just model what an igneous rock would look like if you weathered it, plagioclase weathering and feldspar weathering is going to go along certain trajectories to get your secondary mineral assemblage. So we're going to use CIA as our value for weathering, and we're going to explore different variables. And the first one we're going to explore is grain size. So we have grain size here plotted going from larger grain sizes. This is in phi scale, so going from pebbles to kind of from left to right, pebbles to clay size fraction against our CIA values here. And these are two sites that I've did some field work in. And what we can see is that chemical weathering is most extreme in the clay size fraction. And this fraction provides the most information on climatic influences. So if we look at Idaho, the CIA values are higher than what we see in Iceland. Presumably, this is something to do with the environment, which we're going to further explore. And so I always throw up this kind of quote here that the mud tells it all, and that most of our history is written in the mud language. But as you'll see, it's very complex and not as easy as it looks sometimes when you just pick up some mud. So I like that quote to keep inspiring me to look at the mud. Anyways, we'll look at variables impacting chemical weathering here, and the CIA is always going to be on the y-axis. And we have different variables here on the and the x-axis, and we have elevation, depositional environment, and distance from the source. If we first look at elevation all the way on the left here, we can see that there is a positive correlation for stream sediments in warm environments going from elevation. So lower elevations are not as weathered as higher elevations. However, it's inversely correlated for weathering profiles in cold terrains, and that's because it's just exceedingly cold. So at higher or lower elevations, or at higher elevations, you have lower CIA values because it's just too cold. Then if we go to depositional site here, and this is really just talking about kind of stream beds versus floodplains, so kind of where you store these sediments along the transportation pathway, there is a correlation. So this suggests that there is continued alteration when you put sediments onto a temporary storage site, but it's not perfect. We do see that even older floodplains have a range of CIA values here. And so while there is a relationship here, it's not the single driver. Then if we go to distance traveled, and so this is how far away you are from the source, we can see that distance traveled does have an impact on the clay size fraction here, but it has no impact on the silt size fraction, so coarser grain mud, if you will. And so that's a unique finding, but does this mean that the sediments for this clay fraction are more altered, transported further downstream, or there's continued alteration along this transportation pathway, or potentially both? I think one of the things that's fun about this, the study that we just published in JGR Planets, is that it opens more questions than closes doors. And so there's a lot of research that is hopefully going to come out of this in the future too. But I think this is one area that is potentially something to continue to investigate. Okay, so our next variables here are provenance age, temperature, and precipitation. If we look at provenance age all the way on the left here, and so diamonds, these blue diamonds are fluvial sediments, and weathering profiles are in green squares here. We can see for geological age doesn't appear to have an impact on CI values. And this wasn't intuitive for me. I figured older rocks would be more weathered, which is true. You can see that older rocks are indeed weathered, but you also get even young rocks that are equally as weathered. And so geological age didn't have as much of an impact as I thought it would. I'm going to jump all the way to the right here for precipitation. And precipitation has a scattered relationship with higher mean annual precipitation values suggesting more weathered. However, even lower precipitation values show us a span in chemical index of alteration values. So the relationship isn't as perfect as I anticipated. And then finally, we jump to temperature here. Temperature, mean annual temperature, MAT, and CI are the most strongly correlated variables that we've investigated in this study. And it suggests that warmer temperatures produce higher CIA values in mafic terrains. This is kind of an intuitive thing to understand, but we needed to do this to publish this, to kind of have it in the literature that this is indeed what we're seeing with our fluvial and weathering profile sediments. And it's saying that temperature is the winner here for the variable, and that it's definitely more complex, and all these variables are intermixed, and there's more variables that weren't considered. But for the sake of the study and simplicity, comparing to Mars, we're going to go with temperature as being our controlling variable to develop our paleoclimate reconstructions. And so we're going back to Gale crater with Curiosity, and we're going to use APXS data. This is X-ray fluorescent data that gives elemental data from Curiosity, and our ChemIn data. I don't think I'm going to detail the ChemIn data here, but it is in the publication if you want to go to it. And we're going to look at earlier in the traverse of Curiosity, looking at mudstones from Yellowknife Bay and Pahrump Hills. They're over here on the stratigraphic column, and we're going to compare them to our terrestrial reference frame. And when we plot the CIA values versus mean annual temperature for our fluvial and weathering profile sediments, we see our linear array here. And then if we just take the CIA values for Pahrump Hills and Sheepbed, and we plot their range across any mean annual temperature that we've seen on Earth, we can start to develop a terrestrial reference frame for what the climate might have been when these were formed. And this is really saying that the terrestrial sediments indicate that the paleoclimate around Gale crater shifted from a polar-like climate to a subpolar climate. So going from something Antarctica-like to something more Icelandic-like, going from the Sheepbed, which have a lower CIA value, to the Pahrump Hills, which have a higher CIA values, showing that the climate was variable, but likely cold, and that Iceland is probably a pretty good analog for doing some of our terrestrial analog work. And so where do we go from here? We have, our different representation of a sources sink model here. And we saw that we explored water. We saw water was on Mars. With Curiosity, we explored habitability. But our next mission here is to explore life. And that's really what Perseverance is dedicated to, and hopefully what Mars Sample Return will explore as well in the samples that we get back eventually. And so where do we go to explore life? This is just kind of where organic matter is preserved in the sources sink system. These values are from Hedges and Kyle, 1995. But you'll see outside of a shelf, deltas do a great job of preserving organic matter. And that's just where the Perseverance rover is going. And I love this image of a mosaic that Justin Cohart from Stony Brook University put together of Jezero crater with the delta up here in the upper reaches, or on the left side of the crater here. And Perseverance is an astrobiological explorer of the terrains. It's got a unique payload of instruments to explore Jezero crater with. And one of the fun things for me is that Jezero crater is a delta, and it's clay rich that we've identified from orbit. And so right in the wheelhouse of continuing to look at clays and continuing to look at fluvial processes in basaltic terrains. And so this is where we're going with Perseverance. And in the meantime, we're going to continue to prepare with terrestrial analogs, and that's working in Iceland as part of the Sandy and NASA SSW that we got to go back to Iceland to look at sedimentary processes in these terrains. And we're going to develop best practices for looking at these materials. They are going to be some of the most precious materials we ever get. So we need the best instruments to look at them. And on the right is some of the work that we're doing at Brookhaven National Lab with synchrotron radiation to get X-ray diffraction, as well as pair distribution functions to understand what's going on in this material, just showing comparison with XRD data from Mars down here. And so we're going to continue to explore these novel, not necessarily novel, but higher resolution techniques to look at with our more precious samples here. And we'll continue to get ready for the Mars samples to return and we'll build our understanding of any sources of contamination as we prepare for these to come back as well. And so I'll finish with some final thoughts here and look back. This is a really cool mosaic that Curiosity took looking back at where it traversed already. And so we're sitting on top of Rubin Ridge here. We're looking back at the crater rim here, and we can just sit back and reflect on where we've been and where we're going. And the final thoughts I have here are terrestrial analogs are critical for interpreting the sedimentary rock record of Mars. The results are twofold in the sense that early Mars predates our sedimentary rock record on Earth, so we're understanding what's going on with water in the solar system before we have evidence of that on Earth. But also the sedimentary or the processes that are happening on Earth right now may give us clues to what happened on ancient Mars, and so the results are twofold there. And the future of Mars exploration is exciting, and we have to start preparing now. And that's just what I'm doing. I can't wait to get back in the lab. Seems like we're getting back to normal here soon. And I'll throw out my contact information here. Please feel free to reach out whenever. I love talking about this stuff, and I appreciate you inviting me, and I appreciate you for your time, and thank you very much.
Awesome. Thanks so much, Mike. That was a great talk.
Thank you.
So if you have questions for Mike, please feel free to type them into the chat and I'll read them off. Alternately, you can unmute your mic and ask Mike directly. So David Carl, TU Berlin, asks, could you talk a little more about the kinds of smectites that Curiosity found? Does the rover have other instruments to differentiate the clays further? And if not, is this something that NASA is planning to look at with Perseverance?
Yeah, that's exciting to talk about because most of the smectites we've identified are, one, they are ranging from dioctahedral to trioctahedral smectites, and they tend to be very iron and magnesium rich smectites. And the rover itself does have another instrument that helps us identify this as well. And that instrument is a evolved gas analyzer, part of the SAM instrument, which is also confirming what we're seeing on the different water releases that are within these clays. And the smectites I'll also note here are collapsed smectites. And so that is that the inner layer is collapsed, whether that happens on the surface because it's a desiccating environment or in the Chemin instrument is still potentially being evaluated. But nonetheless, they're collapsed smectites with that main peak at 10 angstroms. Does that help your question, David? Thumbs up. Should I stop presenting so people can see my face, or should I keep it up so that I can flip back to slides?
Your choice.
Okay. I'll leave it up in case people want to see slides.
Well, so we have a question in chat. What are the sources of sulfates and processes involved in their formation? Yeah,
so the sulfates are, we can get sulfuric gases from volcanoes, and then maybe that's precipitating into the waters, and then you have late stage fluids that are coming and interacting and precipitating these sulfates. I think that's part of what's going on here. And that's kind of the extent of where I've gone into sulfates, but we have a number of individuals on the team who specialize in iron sulfates and this continuity, or if you noticed in the graphic of Mount Sharp, it went from kind of clay-rich strata to sulfate-rich strata. And before landing in Gale crater, that was speculated to be kind of a transition in the climate, going from a more wet climate to a more drying climate. So as you're drying, are you creating more sulfur-rich fluids as well? And so we are just about to touch down into the sulfate unit soon. So I think there's going to be more information to come from Curiosity's traverse into the sulfate-rich terrain.
Awesome. So I have a question, but possibly a naive question. I'm not really up on the sedimentary processes, but what role would you expect the perchlorate to play with these minerals? Would you expect it to be bound up in it with any of these clays?
That is a good question, and I'm not going to pretend that I know the answer. I'm going to flip it into a naive response because I'm not familiar with prochlorates
Fair
all
enough.
that much. But we don't, I think we haven't identified prochlorates in the mineral assemblage in over like in an abundance. It's normally below detection limit for chemin. And so if it is there, maybe it is bound to the surface of clays. But it's also, I think perchlorates, there's a couple different thoughts on when they formed, if they're ancient or if they're more of a modern process. I'm not sure which way I'm leaning because I would need to do some more research on it, but I think I'm leaning that they're more modern. And so maybe not in some of these kind of ancient clays that are formed. But I can get back to you with a better answer one day.
We've got a question from Kendall Lynch from LPI. Great talk. How do you take into account the possible secondary processes that may have occurred due to late stage groundwater movement through the sediments? In other words, how can we delineate the source to sink processes during the lake life cycle from possible secondary emplacement processes that may have occurred from post-lake groundwater flow?
Yeah, kind of great question, because that's why I said some of this work opens up more areas of research too, because I don't think that in basaltic terrains has been studied enough what's going on here. And that's what I want to tackle with some of our recent funding to go to Iceland for our SSW, is that we're taking drill cores to look at lake waters mixing with groundwaters discharging. And it's been studied a little bit in more of the marine science field on what this is in terms of creating these unique geochemical gradients. And you see different precipitations in the sediments, but it hasn't been detailed the way that I think to my knowledge, it might be detailed. So I don't mean to offend anybody if they have detailed it, but to my knowledge, it hasn't been detailed in basaltic environments with the kind of precision that we need to identify what those are. And so unraveling what is kind of, if you want to call a first stage sedimentary process from kind of the source to sink before you get to the sink, sorting, whether it's chemical alteration, orthogenesis versus kind of early diagenesis, is going to be, I think, a story that is unraveling with continued work. I would suspect that the clay mineral assemblages would change. I would expect that the elemental composition would change too. And that's something that I'm playing around with a little bit more, is to kind of plot elemental composition to see if we can identify what is terrestrial versus orthogenic in these various environments, and trying to build with more terrestrial analogs for extrapolating this to Mars.
Great.
Oh, Kendra responded on the yeah, she's perfect analog for chlorates here. Thanks, Kendra.
I have a question from Jeff Berger. Great talk. Can you comment on correcting for calcium, potassium, and sodium-bearing salts in the APXS data?
Yeah, Jeff, this is tough because there's a bunch of calcium sulfates that are intermixed with the sedimentary rocks that we see. It was easier, I believe, earlier in the mission. That's why that paper that we looked at, excuse me, only looked at Pahrump Hills and sheepbed, because it gets a little more intimately mixed, whether it's in the matrix or in the cement of these sedimentary rocks as you go further up. I think earlier on, we were able to kind of just subtract a baseline for calcium sulfates, and we could see areas. We would avoid areas that were either had a vein that was a calcium sulfate vein or other salts over time. But since going higher up into the stratigraphy here, I think that's become more complicated, and that's why the paper is looking at CIA and the newer stuff. I didn't touch as much because it hasn't had its time to be scrutinized by the scientific community enough, and that's something that I definitely will be exploring in my manuscripts that I'm working on too, is what this correction does.
Awesome. Question from Matthew Chochnacki. I apologize if I pronounced that wrong. You mentioned sand and associating with the Green Cube Formation. What are your thoughts on its origin? Alien, fluvial, or some combination?
Yeah, so I think the running hypothesis now is that it is aeolian, and there's different kind of ways in which it was deposited over time, but I think it's aeolian, and it's just a matter of how it was altered is different than what we're seeing in Glen Torridon. So I didn't detail what I think is going on there, but I think it is a groundwater mixing as well, but it's not hitting that salinity solution. And if we believe that greenolite is forming as the mixed layer phyllosilicate, it readily precipitates to magnetite. And so that may be why we're seeing so much magnetite in the green hue pediment. I think it's upwards on, in Edinburgh, one of the drills in the green hue pediment, it was 15 weight percent or so of magnetite. It was, don't quote me on that number, but it was pretty close to in the tens right there around weight percent. So maybe that's one mechanism there.
Excellent. Do you have any other questions in the chat or from the audience?
Thank you, everybody, for your comments too in chat. I really appreciate everybody's encouragement. Good to see you all too.
Awesome. Yeah, it's sometimes hard with these virtual presentations to get a sense for the audience reaction, but I think you got a really great response from everyone. So we really appreciate you and coming here and giving the talk. It was really good.
Yeah, thank you for having me. It's quite an honor. And again, my information's there, so anybody reach out. I'd love to talk more about it.
Excellent. Well, thanks everyone for coming to the talk. There is no scheduled virtual seminar for next week, but we will send out an email announcement when we have our next speaker lined up. Until then, I really appreciate you being here. And again, the future LPI virtual seminars will be held at 3 p.m. Central. Otherwise, we will talk to you all later. Thank you so much for coming. Thank you very much, Mike, for that great talk.
Thanks, guys. Talk to you later.